Welcome back to the KiCAD tutorial series. This is part 4, and in the last video we covered creating our schematic and the USB section, where we looked at hierarchical design in detail. We also explored net classes and how to change the color of schematic nets and adjust the colors depending on the net classes. I also gave a quick overview on creating components. In this video, I've made some progress on the schematic and will focus on net classes and how they affect the PCB design in more detail. I want to focus on why we use net classes and how we can get most out of it on KiCAD. As a note, I'd like to say I've created the project again on KiCAD 9, so I've moved over all the files. So we're starting fresh with the latest version. As before, we're working on the ESP32 drone project, and I've organized the schematics into 4 sheets. The first sheet introduces the project, which you got on the screen now. The second covers the power management with USB input, regulators, and a battery charging circuit. We also have an on-off switch here. The third sheet features the ESP32 microcontroller and a USB to serial converter IC, just because the ESP32 microcontroller that we're using doesn't have built-in USB function. And finally, the fourth sheet includes all the peripherals, so the LEDs, the MPU 6050 accelerometer, and the 4 motors. Before we get started with part 4, a huge thanks to PCB Way for sponsoring this video. If you're designing your own PCBs, use PCB Way to bring your projects to life. With high quality manufacturing, affordable pricing, and fast delivery, PCB Way is the go-to choice for hobbyists and professionals. Need assembly? They've got that covered too, with full PCB assembly services, so you can focus on developing your projects to the next stage. Check them out at PCBWay.com and get started on your next project today. One of the things I really like about PCB Way is their creator community. The creator community has a ton of projects that you can look through and order with a few clicks. As you can see, we've got various different projects that we can basically order ourselves, and I share my projects there too, so make sure you check that out as well. Remember to use my link below for a discount. And now back to the video. In this video, I'm going to look at net classes in a lot more detail, and I'll show you how that influences the PCB design as well. Let's quickly talk about why using net classes for PCB design is important. Net classes allow you to categorize different types of signals in your PCB design to allow you to apply specific rules to them. Instead of manually adjusting the width, the clearance, or wire sizes for each net for the PCB design, you can define a set of rules for an entire group of related signals. This saves time, improves consistency, and prevents design errors, especially if you're working in a large team where communication might be difficult. So with net classes, you can tell the PCB designer, which may be yourself, but you can tell the PCB designer what kind of clearances a net needs, what kind of a track needs to be routed. So for example, let's say you have a USB track, USB data line, then that will need to have a 90 ohm differential impedance, and you want to relay that information to the PCB design side as well. So assigning a net class basically allows the PCB designer to make sure that they are meeting those requirements for the tracks. Now, it is your objective as a schematic designer to inform the PCB design and inform anyone looking at the schematic the design intention and the characteristics of the data lines and the PCB itself. Now, let's say we have another line, as you can see on the schematic now, we have a VBAT line. Now, this is a battery line on my circuit, so again, a LiPo circuit, and this project is running 4 motors, which obviously can run a lot of current. So I need to tell the PCB designer, and I need to tell the people who are looking at the schematic that this is going to be a high current path and this is going to be a high current net, basically. So there's a lot of current flowing down this signal over here. So we've already discussed different signals have different electrical requirements, and net classes allow you to communicate that effectively with a built-in tool into KiCAD and various other ECAD software that you might use. So on KiCAD, with net classes, you can define a set of rules that basically when you go onto the PCB side, controls the thickness of tracks and everything. So if you do a DRC check afterwards, it flags up an error if you are not meeting those requirements. Obviously, it may not be possible to meet the requirements everywhere, such as when you kind of interface with a IC or something for a high current path. Those you can make strategic decisions to ignore them or add a non-DRC check there, basically. Another use for net classes is things like I2C or maybe SPI, which are high-speed signals. They may need to maintain a controlled impedance, or they may emit a lot of noise which you don't want to couple into nearby signals. So they may need extra clearance, or they may need controlled track thicknesses or controlled distances, controlled track lengths, things like that, which net classes allow you to do. Again, the aim is to automate the design rule applications. So when you do a design rule check, it will automatically check all that for you if it's been set up properly. And obviously, if you are using all the net classes properly, then that means that you're going to design a circuit that works properly, and that's going to improve your manufacturability. You can set up your default class so that it's not violating any requirements from, let's say, PCB Way, which is the company that's going to be manufacturing this PCB. So if we set up our default to meet their minimum requirements, which may be their minimum low cost requirements or minimum high cost requirements, that depends on the project itself. So in summary, if you're not using net classes already, I think you should be, especially for more complex designs. Obviously, if you're designing a very simple PCB, then you don't need to use net classes at all. When it gets to a more complex project, I think you should always use net classes to manage your track widths and your design rules, to improve consistency, save time, reduce errors, and help ensure that your board functions correctly at fabrication. So when we set up the rules, we are actively thinking about track thicknesses and things like that. So we want to make sure that we get them right. So now with that out of the way, let's go into KiCAD to see how we can utilize net classes for our benefit and how to use them in KiCAD. If you have any more reasons why net classes are useful, please feel free to share them in the comment section below. I would really appreciate your feedback as well, because I want this to be a community-driven thing, as KiCAD is a open source software, which is very useful for us hobbyists who may not be able to afford the most expensive software that's out on the market. On this schematic now, I don't have any net classes set up. We did set up some previously, but I'm not going to be using them. I'm deleted them and basically started with the new project over here. So the first thing you want to do is go to File, Schematic Setup, and in net classes, I'm going to create 4 net classes for myself. The first net class is going to be USB 90R. The second is going to be high speed, so I'm just going to call that HISP. The second one is going to be high power. I'm going to call that 2A, and then the last one is going to be 1A, which is for 1 amp of current. And the last one you can see is default. So I'm just going to copy over the wire thicknesses because I don't want to change them. I'm not using buses for this project, so we will have a look at them in the future. So with that, we have created our net classes, and now we can assign net classes using this button over here. So place directive label. I can select one of the net classes that we've created. So first one, you can see USB 90R. I'm going to add that to basically this section here. Alternatively, I can add it to this section over here without placing a directive on the schematic itself. So I want anything that has USB in its name to have a USB 90R net class. And in order to do that, I want to place a star first, type USB, and then type star again. So you can see I've got USB DN, USB DE, and I've got them on 2 different pages. I've got USB on ESP32 page, and I've got USB on the power management page as well. Then I'm going to change the net class to USB 90R and press OK. Now you can see I've got resolved net class as USB 90R. Slightly better way of doing it would be to rearrange this part over here so that I create more space. So let me move this down here somewhere, and then add the directive flag. And the reason this is slightly better is that if you print off the schematic for review and someone else is looking at the schematic itself, then they will be able to see the directive as well. Whereas the other way we just did, it's only visible if you are looking at the schematic in KiCAD, which is not always possible. The schematic might be reviewed by someone else, and they may do a paper review rather than a review on the software. One of the new features with KiCAD 9 is that you don't have to change the color of the net itself, but you can put a highlight around the net, which is something similar to Altium, and I prefer that method with the highlight. In order to enable that method, you basically have to go to Preferences, click Preferences again, go to Schematic Editor, display options and then tick this checkbox over here. Then we can turn down the thickness if we need to, and we can turn down the opacity if we need to as well. But obviously that's down to your individual preference. So you can see around the green net, which is basically this wire over here, we've got a blue highlight for our USB 90R. Now what I'm going to do is add the net classes to all my net labels that need them. So obviously you got the USB 90R. I also want the high speed net, which is the I2C. And that's these two lines over here. I'm going to drag that out. I'm going to assign them with a net class by placing a directive. And for that, I want high speed. I'm going to copy this and place the same net on the clock line as well. Now we haven't done anything with this net class yet. So if you go into our schematic setup again, go to high speed, and let's say we select a color for that. I'm going to choose maybe orange, press OK, and press OK. You can see that net class has a orange glow to it now. And anywhere where the SDA and the SCL sign will appear, those nets will change as well. I'm just going to confirm if the same is happening on the peripheral side, which you can see it's not. So this is where it's debatable if you want to change it in here. So if I was to assign it over here, the net class would apply across the sheets, but obviously it depends on the way I apply it. So if I do believe that is a graphical glitch, which we fixed by deleting. So I'm not sure what was going wrong there. This net class, without placing the flags on it, has got this. I think a safer option is just to put the flag on it, basically. So again, for the same reason we discussed before, is if you're doing a paper review, then it's easier to see. Now the other net class was the high power. And this part of the circuit over here is for the motor control, which is going to draw a lot of current. So for that, I'm going to put down the 2 amp net. Now, obviously, I'm not entirely sure if there's 2 amps that is going to be drawn here. It doesn't really matter because this is just for learning KiCAD anyway. So 2 amp on this label, and we can rotate that if we want to as well. I think that's kind of down to preference. We're going to have 1 amp coming through here. And that is mainly for the charging circuit. VBAT again is going to have 2 amps. So I'm going to go back to my peripheral sheet. I'm going to copy this and place the 2 amps over here. As you can see, VBus is also going to be 1 amp, just because that's also going to the TP4056. So far, we have configured VBus, the 5-volt line, the VBAT line, and the motors basically line over here. But another thing you need to remember, or I need to remember, is the current that's flowing down here is also going through this path. So we need to make sure that we apply this net to any path which is going to have a lot of current flowing down it. This will also apply to the ground. I think we're a lot more relaxed with ground, so I can delete it because I will probably just end up putting a ground plane anyway. If you don't have a ground plane and you need to make sure that you're routing at least 2 amps for the certain tracks that you need to, then you need to manage that a little bit more carefully. So the last thing I'm going to do is go into my editor. I want to change the colors for all the tracks that I just did. So one of them I can set as green, and the other one, let's say we set as red. And the default, I don't really care about. You can see all the VBAT tracks are basically green. The VBus is red, but looks like orange to me. So I don't want to avoid electronics completely in this video. So let me just quickly explain to you why I have set up these net classes so that they make more sense in context. First of all, USB 90R. So when you're using USB data lines, there is a requirement for USB to have a 90 ohms impedance. Basically indicates to me or the PCB designer that the tracks will need a controlled impedance for the routing. Now, controlled impedance for 90 ohms basically means that you need to control the thickness of the tracks. So for a differential pair such as the USB line, you want to have a control over the width of the track, the separation between the differential positive and the differential negative, and the height of the dielectric, basically where the next power plane is. So that might be a ground plane or a power plane. So these are the rules that you need to define for USB 90R net class in PCB design. So the width, the separation. The height is obviously controlled by the manufacturing process, but we can dictate that when we set up our design rules. Now the PCB designer, let's say someone else, then they can decide the track width is going to be too much or that they don't need a full layer track. They can make design decisions based on the requirements as long as it meets the 90 ohm requirements that you've specified on the schematic editor. The high-speed net class on my schematic at the moment is only used for the I2C data line over here, which is talking to the MPU 6050, which is a accelerometer. My main objective is to have a clearance from these tracks to any other tracks that might be sensitive. As you can see on this board over here, we don't have anything analog, so that's not going to be too much of an issue, except for maybe BAT VCD. So if these tracks are running close to this track, I want to make sure that I leave sufficient clearance, and I can define that in the design rules. The other two are kind of self-explanatory. They're basically denoting high current paths in the circuit itself. So 2 amps and 1 amp. For the PCB design rule, the main thing that's going to dictate is the track thickness. Now, sometimes the voltage drop might be important as well. Then you can communicate those types of rules with a design note as well on the schematic. In the last video, I did say I'll go through design notes, but I think this video is going to be long enough anyway, so I'll leave that off for another video. But essentially, this is what I mean. It's basically placing a note on the schematic itself that conveys some message to either yourself or someone else that's going to be looking at the schematic or the PCB design. And it's supposed to clarify certain design decisions that you've made on the schematic. So there might have been certain things that you needed to look up when you designed the schematic, and those things are important. Now on this schematic, I've just basically placed down some design notes that involve around calculations. So you can see I've got a brief design note over here which shows the ADC pin voltage. So this is useful when you come to actually doing your software and evaluating if this voltage is going to be suitable for the microcontroller that you're using. So you can see this is going to go from 1.6 volts to 2.1 volts. And our battery voltage is going to go from 4.2 to 3.2. So we have a 2-to-1 divider over here. Now, because it's going only up to 2.1, we're going to be fine with the microcontroller. The other design note I've got here is a charging current calculation for TP4056. And I've basically got this from the datasheet. Now, if I wanted to modify this, I've got the equation right here, and I can change that around if I need to. So let's say I wasn't using 1K3 resistor over here, and I had a slightly different resistor somewhere else, which I wanted to use instead of a specific one that I was using here. Then I can change that around, do a quick calculation to make sure I'm still under the limit. To create a design note, I basically use this text box, draw test box function over here. So you can select draw a text box, and in there you can type in your design note. And if you wanted to fill in a color, which can be quite useful, is you basically click the background fill button, select the color that you want. I quite like yellow. I suppose I'm just used to Altium. Press OK, and you can see you've got a text box with a background color. We can have a look at the design notes in a bit more detail in another video. For now, I want to focus on the net classes. So we can see we've set up all the net classes that we need. I'm going to open the PCB editor. And to do that, I'm basically going to click this button over here. Next, I'm going to bring in all the changes from my schematic side by pressing this button, update PCB, and you can see I've got all my components over here. And this has happened because I manage my libraries a little bit differently to how KiCAD expects you to manage your libraries, or has the default library management settings, I would say, rather than expects you to manage your libraries. Again, I will make another video on how to manage your libraries with a proper design workflow included as well, because I think that's important. So now what we're going to do is use those net classes that we set up on the schematic side to control the design parameters on the PCB side. So if you go to your board setup, which is over here, if you go to net classes, you can see all the net classes that we created on the schematic side also appear over here. First of all, I'm just going to fill in the differential pair bits because I know these are not going to need a differential pair. I'm never going to use microwires as well. Now, all of these calculations, such as the clearance, track width, wire size, wire hole, can be influenced by your manufacturer of the PCB, as well as what you need from the PCB or from the tracks that you're designing. So for example, for the 2 amp tracks, I know from experience, I think we'll need like 0.8 mil tracks, 0.8 millimeter tracks. So that's what I'm going to put down. But for your USB 90R, which is a differential pair, where you have the differential pair width and the differential pair gap, is basically similar to the differential pair graphic that I showed you earlier. So I'm going to fill in all this information now. So at this point, it's quite useful to go onto your KiCAD and use the calculator tool. For starters, I'm going to use the tool for the high current nets. If you go to your KiCAD homepage, press calculator tools, and you go to track width, and let's say we have a 2 amp track, temperature rise 10 degrees. Now the conductor length dictates the voltage drop, so it's not going to dictate the temperature rise of the track. For my case, I don't really care about the voltage drop, so I'm just going to leave that as 50. And you can see I've got a 0.78 track over here. So what I'm going to do is go into my 2 amp and put down 0.78. Now for my 1 amp tracks, I need 0.3. I can do the same thing for the wire sizes, which I know these are a lot more relaxed, so I don't think we'll have any problems. So D, let's put down as 0.3, which is the default, and the pad diameter is 0.6. And you can see that gives us a capacity of 2.4 amps. So we'll be fine with that. So I'm just going to copy these onto all my tracks. The high-speed track, I don't need anything special for them in terms of track width. So I'm just going to copy that as well. For my high current paths, I don't need extra clearances, so that's fine. So I can fill that in as my default. For high-speed tracks, you typically want to keep a clearance of at least 3 times the trace width. So in our case, you can see our trace width is 0.2 for the high-speed track. Now 0.6 might be a little bit overkill, but I'm going to place that as 0.6 clearance. Now the only thing we need to sort out is the USB 90R. For that, we need to go into the PCB Way website. We need to look at the capabilities. So on the PCB Way website, and other PCB manufacturers also will have a stack up and a impedance calculation. So for a full AL PCB that's 1.6 millimeters thick with a 1 ounce copper inner and 1 ounce copper outer as well, you basically get this layer stack up, which gives you the DK value, which is what you need, and the thickness of the dielectric, which is this green part over here. For a differential pair, we want to use this. I want to change all my dimensions to millimeters. And let's start off with something basic like 0.2, 0.2, and the thickness or the height we get from over here, which is 0.196, and the ER is 4.74. So you can see I've got a differential impedance of 90 ohms. So for a differential pair, you typically want to get Z diff to be 90 ohms, and I think Z naught you want to try to get to 45 ohms. So you can do that using this PCB Way tool over here. And you can see I've just played around with the numbers a little bit. So the track width I've put down as 0.3. The separation, the S value I've put down as 0.15. And I've got very close, 42 and 84. Now you can see with my calculations over here with a separation of 0.15 and a track width of 0.35. I've got a differential impedance of 90. And I've got a Z naught of 45. Now you can do the same calculation on KiCAD as well. So if I put in those numbers over here, you can see if I press the analyze button, I've put in the parameters for the dielectric material, which is down here. The thickness can vary. So you can see there's two numbers here. The thickness after lamination is probably what's important. And if I press the analyze button on that, you got slightly different numbers, but I think that will be okay. Now I've used 0.3 and 0.15 in the past, but all the calculators give slightly different results. So that's something that you basically need to communicate with your PCB supplier to make sure that you're getting that right. So if you want something specific, impedance controlled, you need to speak with your PCB supplier and let them know that, for example, let's say in this case is 0.3 tracks. Then let them know that 0.3 tracks need to be impedance controlled to a differential impedance of 90 ohms. And they will basically advise you on how to do that. And they will tune their processes and materials for you to be able to meet that, if possible, obviously. Now, USB 2.0 is not that sensitive anyway, so you can basically ignore it. For signals that are more sensitive, you'll need to make sure you get your impedance calculations correct, and you should communicate that with your PCB manufacturing place as well. So what I'm going to do now is go into my board setup, set up the clearance as that, and the default track I can set up as that because it's the differential pair that I really care about. So the width of the track is going to be 0.3 and the gap is going to be 0.15 as we just did on our calculations. Press OK and that should be okay. So now, just to show you, I'm going to grab my USB-C connector. I'm going to grab the USB to serial converter, which basically takes in the USB-C signal. So that reminds me, I've forgotten to do one thing on the schematic side. So if I go back to my schematic editor and I go back to my main page, you can see I've not connected up the nets between the schematics. So what I need to do in order to do that is click on the symbol itself for that sheet. So that's power management. And what I'm going to do is press the sync sheet pins button. And I've got 3 pins in there that I need to sync over. So I've got BAT VDC, I've got USB DN and USB DP. Press OK. And on this sheet, do the same thing again. USB DP, USB DN. Now the SDA is going to go on the peripheral side. Also have some LEDs and motors. I think this is a new feature with KiCAD 9 in that you got all this green, which means all the sheet pins are synced over. I can press the close button on that. And then next, I need to basically just connect them up. You can see I've got all the connections made now. If I go back to my PCB design and press the update button, I should have my connection from here to here done. Now, last time we looked at USB D and DP, the naming of differential pairs. So I'm going to place a differential pair on here. And you can see I've basically start off with a violation. And that's because I don't have enough clearance on this pin to meet this gap over here. But if I start it from here, it will be okay for this case. I'll run into the same problem on this side. As you can see, there's not enough clearance to the ground pin over here. Now to go around that, I can basically add the remainder of the track manually. Or I can go into my settings and then change some settings that allow me to route with violations in place. And in order to do that, you basically want to press highlight collisions and allow DRC violations. So now if I go and place my track again, you can see that it's placing fine, but it's showing me an error, which is exactly what I want. But the purpose or the good thing about this is that we are doing this intentionally. So we are basically aware that we need to change the track sizes over here. Now for the end bit, I don't want a 0.3 track because it's slightly getting closer to this pin. So what I can do is predefine another size. Let's say I add in a 0.2 track in there. I go to my track. Rather than use net class width, I'm going to use the 0.2 track and then I'm just going to route that manually. It's still going to show me the error, but this is going to be a smaller track than the pad, which is what I want. Now the same thing will apply here as well. So I'm happy with these tracks because the pads are thicker. Now for this particular track, I'll need to add in some wires as well. So that makes it a bit awkward, but that's just because of the way this is aligned. Now another thing we can do for, let's say we are placing the track for the motor, then we have a connector, we have a transistor. So let's get them close. We have a diode. Ideally, I want to keep close to the motor itself. The 10K resistor, which I don't really care about for this demonstration. So let's just do something simple like this. We know we have a high current path over here, and we've done that in green. So what we can do on this side is basically go to our net, and then we have our net classes down here, and we have all our nets over here. We can change the color of nets individually. So let's say we have a random net, so net D3A. We can change the color of that net to red, let's say. And you can see this rat nest over here has gone to red, which is basically connecting all these components. So the net itself, or the rat nest, goes to the color that we set here. However, we can do that with our net classes, which is a lot more useful. So we have, let me delete all of this. So we have set up a bunch of nets in the past. I'm just going to use 2 amps as the example. So obviously on the other side, as in the schematic, we had green. So I'm going to use green on this side as well. So you can see all the net classes with the 2 amp label have gone to green. And that's basically all the VBAT symbols in this case, as well as the tracks down here. So it's not just VBAT, it's VBAT plus whatever this track is. So in this case, that's D3A. So luckily the same track that we picked before. So to reiterate, this allows you to change the color of the rat nest. If you go into your board setup and you go to your net classes, you can see that is also changed over here. Now let's do the same thing for the high speed. Now on the schematic side, I think the high speed net was purple or pink. So I'm just going to go into here, change that to purple, press OK, and you can see all the high speed nets have been given the same purple color. Now, if I remember correctly, in KiCAD 8, it did change the color of the tracks itself as well to the color that was set here, which it doesn't do anymore. And I think that's a good thing because it made it a bit confusing to use. And I think it's a lot better the way it's done now. Now, if you have problems with selecting different things, you have a selection filter over here, which I've just moved here because I wasn't able to change the size down here. And I can turn off different things. So for example, text. So I was trying to select this component and I was accidentally selecting the fabrication note, which I didn't want to do, and it won't let me do that anymore. So I've turned off text basically. So I can't select R18, I can't select R17, things like that. I can still select my components. Now you can see over here that we've got our 0.6 clearance basically for this track. And if we were to do another track that has the default net class, that clearance is less. So let me just click on this pad and you can see that the net class for this is default and the net class for this is high speed, which gives you the different rules managed automatically. Now, when we need to route this track, we can basically make sure that the clearance is good. And obviously you're going to have problems when routing this, but that's okay because we are doing that intentionally. Now, what I would do is once you've routed the kind of tracks that are causing the problems, I'd go back to the settings, so root interactive router settings, and turn this off. So I would turn off allow DRC violations and press OK. You can change this, by the way, to shove tracks around and things like that, which is quite a useful thing, really. So this just highlights where you're causing a violation. If you change that setting, let's say to shove, press OK, and then you do that same route again, you can see it moves that track out of the way, which I personally don't like, but some people might prefer. The last setting, which is walk around, and I think that's the normal setting, basically goes around the track itself. And this is the default one. So let's just do this final net, which you can see the clearance for. And it won't let me route this properly because I've turned off the settings. So if I go back into my settings, allow DRC violations, and then route this out like this. So basically I want to move away from this track as quick as possible, and that should be okay for me. Go back into interactive settings and do the walk around. And now it's automatically managing the clearance of 0.6, which I have set in my rules. Now this is probably overkill for I2C, but this is just a demonstration of how net classes work in KiCAD. In today's video, we have gone through net classes in a lot more detail and how it affects the PCB design side, how we can use net classes to our advantage in order to reduce errors, and basically a form of automatic rule checking. In the background, not on video, I've completed the schematic itself, but I've not used anything new in order to do that. So basically video 3 and this video you can use to get to where I am in terms of this PCB design. So you've got the power management again, you've got the ESP32 microcontroller and the USB to serial converter. You've got the peripherals, which is basically the 4 motors and the accelerometer, the LEDs. And then you've got the front page with a block diagram and all the sheets that we need for this design. I'm trying to go a little bit slower. So I've had some feedback from you guys and I'm trying to go a little bit slower in order to explain what I'm doing in a bit more detail. Hopefully it's worked, but when you're kind of familiar with things, it is harder to break it down into smaller steps that you might not realize that other people may not necessarily know. So apologies if I'm still doing that, but I'm going to try and improve that as much as I can and basically go in smaller steps in order to explain this in more detail for you guys. In the next video, I'm going to go through bill of materials management and PCB design workflow, which is an interesting topic. Now, if I basically delete all of this and bring in my components, I say something like this, place that down here and show you a 3D viewer of this. You can see all my components have a 3D model. They're all slightly different to the KiCAD default models as well. And I've tried to find 3D models where I can. It's not always possible to find a 3D model for components. If that's the case, then you can just create a block on FreeCAD or something as a substitute. Now you can basically export this to FreeCAD and print it out with a 3D printer if you need to. And it's quite good at those kind of things. So you're checking heights, component clearances and things like that, making sure that it's going to fit in your box. The reason why I create my own components is basically this. So if I go to my print button and show you a print preview of my schematic, it's going to look like this. So you've got all the component labels. You've got all the pin 1 indications and things like that as well on the board. And essentially what this is an assembly drawing. So if you're transferring this, let's say in your business for someone to assemble, or if you're sending this off to a PCB assembler, then this drawing is very useful for them in order to create the board for you. So it's very easy to create this drawing if you are basically managing your own libraries. Now with the default components, the fabrication layer is all over the place, so I don't quite like it. So I manage my own basically. But in the next video, I'll show you how to do that. So here is an example of the default component, which obviously I've forgotten to delete. Now the reference, the value basically gets added to the fabrication layer. You can use a different layer as well if you want to for your assembly drawings. Fabrication layer for me is the easiest to use, and I'll show you this in a lot more detail in the next video. Now imagine this for every single component in here, and it gets very messy when you print it out. With your own footprints, you can delete those and you can manage it in your own way. So thank you for watching today. Bye for now.